Okay, this video is going to help you answer task 4, which is where we are going to examine the use of chi-square, which is a statistical test used to analyze data. Now, the data has to be gathered into categories, and we have to see if there is some kind of difference in those categories. So let's just have first of all, a think about whether we have a suitable test or not for chi-square before going ahead and actually using it. And to do that, we have to think about what the study is. So we are completing a study, and in this case, it's we want to determine if there's actually a difference in the land use used on two sides of the loch. Because in our previous piece of data gathering, we discovered there was a real noticeable difference in the pie chart. So, for example, rough grazing was only in a relatively small amount on the south side, but it was the dominant land use on the northern side. In contrast, the south-facing side had quite a bit of forestry and crops. In contrast, the crops on the northern side were almost non-existent. So we suspect there's a significant difference, and we're interested in why that might be the case. So let's go back and have a little look at why use chi-square. Well, first of all, if data is categorized, and in this case it is because it's the amount of kilometers in each of the different land uses. So the land uses are the categories, okay? It automatically becomes possible to use chi-square. Now there is one other aspect we need to consider. Do we have at least a minimum of 5 kilometers squared of land used for each of our land uses? Now, if we have a look at our data table, we can see that yes, we do. Even here, we have 5 kilometers squared worth of settlement on the north-facing side of Loch Tay. And that is actually the minimum amount we need in a category, would be 5. Okay, so we've met that basic requirement. We've got 2 categories, north-facing, south-facing, and we've got these 6 subcategories. So we can indeed go ahead and use a chi-square. So when we set up a chi-square, the first thing we have to set up before conducting the test is a null hypothesis. So a null hypothesis is always set up as there is no statistically significant, and this word here is really quite important because in chi-square we're always interested in seeing whether there is a difference between two things. So between the something kilometer squared land use and the something kilometer squared land use on either side of the loch. Okay, so what would that question mark be? Right, now in this case, what we are looking to see if there's a difference is between what we have observed, as in what did we see when we went out there? How many kilometers squared of each of our 6 land uses did we actually measure? Okay, and that's what we call the observed amount. Now, we want to compare to see if there's a difference between what we actually see and what we expect. Okay, now the expected amount should be the same. So what if, assuming there is no difference between the two sides of the loch, we should see the same amount of each of these land uses. Rough grazing should be in equal proportions, forestry should be in equal proportions, and so on. Okay, but we're testing to see whether that is true. So the idea of what you observe and what you expect is a key theme in chi-square, and expected is always should be the same because we're trying to see if there is a difference from the expected. And the observed, of course, is what we see. So that's what these two questions marks are. Right, that's question 1 dealt with. We've formulated our null hypothesis. We now have done our calculations, and this here is the result we have got to, 23.5. And we know it's for 5 degrees of freedom. Now, just to remind you, where do we get that 5 from? Well, actually, the 5 degrees of freedom comes from, you take the number of columns, we have 2 columns of data, and that would become 2, and you do minus 1, so we're left with 1 there, and you multiply that by the rows minus 1. Now we've got 6 rows, we take away 1, so that's 5. So we've now got 5 rows, 1 column, doing our 2 minus 1, so 5 times 1, and that is why our degrees of freedom is 5. Okay? Using the table of critical values below, evaluate the significance of the calculated result in relation to your null hypothesis. Right, now, before we go through what the answers are, we would always have a look at the critical values table. And our result, let's just remind ourselves, 23.5 for 5 degrees of freedom. So there's 5 degrees of freedom down to 5. Is it greater than this? Well, 23.5, yes it is. So now is it greater than the 0.01? Yes it is. So what does that all mean? Well, in basic English, it means that we first of all are rejecting our null hypothesis. Why? Because we've got higher than the required critical value. So step one is to automatically reject the null. If we cannot get our number higher than this for the degrees of freedom that we're working within, then we accept our null hypothesis. And actually, that is the end of your statement. You say nothing more than you have to accept the null hypothesis because the result of, and let's just say it be 9.6, is not greater than the 0.05 significance level, and therefore we accept the null. And by accepting a null, you are basically saying there is no difference between, in this case, my two land uses. But we have got greater than that and that. So we're actually, because we were greater than that level, we are 99% sure that there is a difference between the amount of land use on the two sides of the valley. So let's report this. The result of 23.5 is higher than the critical value of 15.086 for 5 degrees of freedom. We therefore have to, and in this case we reject the null hypothesis. We can therefore, now when you reject, you accept the alternate. Now the alternate is always the opposite of the null, so that there is a difference in the expected and observed land uses. So accept the alternate hypothesis. There is a statistically significant difference between land uses on either side of the log. We can do so at the 0.01 significance level, which means we are, now this always means that we're 99% confident that there's a difference. And in this case, we're talking about the differences in land uses on the north and the south facing side of the valley. This does, however, mean that there is, and we have to write this down, we have to accept there's a 1% chance that our result was just random. So if we did this 100 across 100 valleys, one of those valleys would just have had a random accidental result. Okay, and it's not mathematically connected. Okay, so there we go. We've dealt with this particular question. Hopefully you go write it up, and hopefully that's helping you to start to understand how chi-square is used.